right, next slide, please, Russ. So just a little bit about 3C Ren. If you're not familiar with us, the Tri-County Regional Energy Network is a partnership between San Luis Obispo, Santa Barbara, and Ventura County. We offer services for building professionals and households centered on energy efficiency and workforce development, and we are ratepayer funded. Next slide, please. So we have 3 programs at 3C Ren. Next slide. The program that you are benefiting from today is Energy Code Connect. Energy Code Connect has services for all building professionals. We offer an Energy Code Coach, which is a live field coach that you can access online or through the phone. We have training and support such as the one today, and then we have regional forums. We'll have 2 this year, 1 virtual, all about permitting, and 1 in person later this year about our newer programs. Next slide, please. Another one of our programs is building performance training, another service for building professionals, both active and prospective. It teaches technical skills and soft skills through training and certification programming. Next slide. And then our final program is Home Energy Savings. This is our resident-facing program, which offers incentives and rebates for technical assistance and actual installation of energy-efficient appliances like heat pumps. And if you are interested in being a participating contractor, you can go to 3cren.org/contractor participation to learn more. Next slide. So with that, I'm going to hand it over to Russ to get us started. Thank you, Russ, and thank you all for joining today. And if you have any questions, feel free to just message me in the chat. I will be staff online and available today.
Awesome. Thanks, Gray. Appreciate it. Hi, everyone. It's great to be here. Welcome to everybody. And so this class is a part 1 of 2. Part 2 will be in a couple days on Thursday, same time, same channel. And it's the HVAC design is basically 3 parts: Manual J, Manual S, and Manual D. We'll cover Manual J, load calculations, and Manual S today. And just so you know, this class was originally developed for Sonoma County energy and sustainability programs. Sonoma County is pushing a lot of heat pumps, like a lot of people are. And one of the things that people are finding is that heat pumps are very susceptible to bad design. If you don't design a heat pump system correctly, it's much more likely to have issues. And so it's that much more important that we learn about the proper design. And so that's why you're starting to see a lot of these classes. This is really an introduction to Manual JS and D. There's only so much you can cover in 3 hours. There's 2 1.5-hour classes. Both PG&E and SoCal Edison have much more extensive classes. If you go to the PG&E training website and search for 3D, there's a class that I teach it's 3 days, 3 hours each day, and it covers going through one of the software programs, the 3D software program, and doing design that way. So we'll talk a little bit more about that. But today's class is part 1 of 2. So again, we'll do Manual J and S today, and then part 2 will be this Thursday, and we'll cover Manual D duct design. The agenda for today is we'll do some introduction. We'll talk about some terminology, some definitions, some basic things you need to know in order to do good design. Then we'll talk about an overview of the overall process, what's involved with designing a residential HVAC system. And then we'll dive into the Manual J part, which is load calculations. And then we'll dive into the Manual S part, which is selecting equipment to meet those loads. Then the agenda for Thursday's class, part 2, we'll review some of the stuff we covered today. And then again, we'll review the overall design process, and then we'll focus really on designing duct systems for based on the equipment that we select and the house and all those sorts of things. Okay. All right. So let's get some introductions out of the way. Again, my name is Russ King. I'm a licensed mechanical engineer in 3 states. I'm the CEO of a company called Coded Energy. We're the developers of Quick Model 3D software. That's a new load calc and duct design software for residential. I've been doing HVAC design and energy efficiency consulting for over 30 years. I started back in 1988. I was working on a computer that didn't even have a hard drive back then. My email, feel free to send me emails. I'll have this again at the end, is russ@coded-energy.com. I have an HVAC blog where I get a lot of things off my chest related to HVAC design and stuff like that. It's russellking.me. The website for our software is Quick Model. And then we have a YouTube channel that's got a lot of videos and stuff related to HVAC design, a lot of software demo videos and things like that too. If you just search for Quick Model on the YouTube, you'll see it there. So let's talk about manuals JS&D. First of all, ACCA, ACCA stands for Air Conditioning Contractors of America. It's the largest trade association for HVAC in the United States. They write and publish ANSI approved manuals on residential and non-residential HVAC design. But for residential, they're definitely the most widely recognized as the industry standard for HVAC design. But they're not the only standard, but by far the most common and most popular standard, I would say. The California Energy Code and the California Mechanical Code both require ACCA Manual J, S, and D or equal for all new residential HVAC systems, whether that's a new system in a new house or a new system in an existing house. You're supposed to do a thorough, proper design. More and more building departments are starting to enforce this requirement. It's been in the code at least since the 2013 code, probably even before that. More and more building departments are starting to enforce it, primarily because of the importance of doing good design for heat pumps. But contractors should be doing it anyways. You know, I stress a lot that if you don't do a load calc on a house, you're not measuring that house. And if you're not measuring the house, you're just guessing, okay? Same thing goes for duct design, but primarily for load calculations. You know, you've heard the old rule, measure twice, cut once. I'm probably more of the measure once, cut twice school of thought. But what if you don't measure at all? You're just guessing. You have no idea. And you cannot size equipment based on square footage. I have examples where I show a house and just by rotating the house 90 degrees, I can change the load by like 30%. Just by turning the house 90 degrees. I didn't change the square footage of the house. So it is impossible to properly size equipment based on square footage of the house, okay? Windows has way more impact on a house's load than the square footage, than conditioned square footage. So if anything, size it based on square footage of windows, okay? Don't do it square footage of home. Anyways, do a load calculation is what I'm really getting at. So manual JS and D are the three main design manuals. ACCA has a whole bunch of other ones too. Manual RS is kind of an overview. Manual T goes into selection of terminals or registers. Manual H is specific to heat pumps. And there's a new one out called Manual LLH, which stands for low load homes. And that is as houses get more and more efficient, like these passive homes and things like that, the house gets super efficient. How do you properly size an HVAC system that's going to cool and heat that house adequately when the load is so small? All right, and then there's some really good standards. These I highly recommend you look into the ACCA QI standard. I believe it's called Standard 5, but just search for ACCA QI standard. Those are free PDF downloads, and it's just a checklist of all the things you really should do to do proper installation, and it includes doing a design first. Okay, and then ACCA.org is their website. So all this stuff is available from their website. Let's see. Checking to see if we got any questions. Let's go. All right, so really basic definitions. BTUs, air conditioners, heat pumps, furnaces, they're all rated in BTUs per hour. What exactly is a BTU? Well, it's a unit of heat energy that is approximately equal to the amount of heat stored in a wooden kitchen match. So if you take a match and you burn it, you let it burn all the way down to the nub, you've just released 1 BTU of heat into the air. So if you think of an air conditioner that moves 18,000 BTUs per hour, that means it extracts 18,000 kitchen matches worth of heat out of the house in 1 hour, or 36,000 or 48,000 or whatever the capacity of that air conditioner is. Same thing with furnaces. You have 120,000 BTU furnace is putting 120,000 kitchen matches worth of heat into the house in 1 hour. And then of course we express that rate of movement as BTUs per hour. So BTUH is what we rate equipment at. The cooling load is, well, in the summer, the BTUs are more concentrated outside. So they're going to want to come into the house. So the load is how many BTUs are coming into the house naturally by convection, conduction, radiation that we need to remove in order to keep the house cool. All right. And so we call that the load. That's a number that can be calculated on the house. When you cool something, that is removing BTUs. That is the opposite of load is cooling, is you're pulling out BTUs that are coming in. All right. And so I gave the example of kitchen matches already. And then heating load is the BTUs are more concentrated inside the house in the wintertime and they want to escape. They're going to try to get outside. And so you can calculate how fast that's going to happen by looking at the delta T's, the inside temperature, the outside temperature, how much is the house leaking, how much insulation is on the house, and that sort of stuff. But that's a number you can calculate. So that's the BTUs escaping from the house. And then we heat a house, we replace those BTUs in order to keep the house at a constant temperature, okay? So to maintain a constant temperature in a house, the amount of BTUs coming in has to equal the amount of BTUs leaking out. I have this great analogy I use in some of my classes about why a house is like a tank of water. So if you imagine a tank of water and it's leaking, water's leaking out, in order to maintain a constant level of water in the house, which represents temperature, you have to replace the water at the same rate that it's leaking out. The same thing is true of a house. In order to maintain a constant temperature in the house, you have to replace the BTUs at the same rate they're coming out, or in the summertime, you have to extract BTUs at the same rate that they're coming in, okay? So it's all about supply and demand. The capacity of the equipment, how much BTUs it can put into the house or how much BTUs it can take out of the house, that's the capacity of the equipment. Think of that as the supply, what the equipment gives you. And then the load is the demand. That's what the house needs. So you can calculate that load and then find a piece of equipment with the capacity to provide the supply. So supply and demand, think of it in those terms. Good equipment sizing is the ability to match the equipment supply to the house's demand, all right? And you can definitely be too big and you can definitely be too small. So there's kind of a sweet spot there, depending on the equipment that's available as to getting that capacity to properly match the house's load. And but if you don't do a load, this is all the wild, wild west and you're just guessing. So it's really, really important to do a load calc on a house so you know how big to size the equipment. Now, undersizing is defined as when the capacity of the equipment is less than the load of the house at design conditions. Okay, so the equipment's a little small and it can't keep up when it's a certain temperature outside. We call that undersizing. Oops. Oversizing is the opposite. It's when the capacity of the equipment is a little bigger than the load of the house. So the equipment is bigger, the capacity of the equipment is more than the load of the house at design conditions, okay? But you can definitely be too big, all right? And then I mentioned design conditions. So design conditions are the specific indoor and outdoor temperatures at which those loads are calculated. These are not the very worst temperatures on record. So for example, I'm up here in the Sacramento area and the summer design temperature is 98. And I think last year it had 110 last summer. So why are we designing to 98 degrees when it hits 110? Because it only hits 110 for a very short period of time. They said, oh, we hit 110 3 days. That doesn't mean it was 110 for 3 solid days. No, the temperature peaked at 110 degrees. And the actual load of the house does not follow the temperature. It lags behind the temperature. And so when the temperature peaks, that load never is the same as though it was 110 degrees. All right. We have thermal mass in our house and things like that. And there's other things you can do to take that into account. All right. Don't mess around with the design temperatures. People say, oh, it's 98. I'm going to design to 105 because I know it's going to get that hot. Don't do that. That is not allowed by code. All right. We pick those temperatures very specifically. Well, I don't pick them. Somebody picks them. They're called the 99th percentile temperatures. Okay. So it would not be wise to design to really high temperatures, because now your equipment is potentially oversized. And then on the mild days, it's not going to work very well. It's mild more often than it's hot. Okay. In fact, we call it the 99 percentile day. The temperatures, the design temperature is a 99 percentile. That means it's only hotter than that temperature 1% of the time. So 99% of the time, it's that temperature or less. We design to that 99. We don't design to the 1%. Okay, it's not worth it. And hopefully I've got some examples here that'll convince you that oversizing equipment will cause more comfort complaints than undersizing equipment. And if you don't believe me, go to the YouTube channel, Quick Model YouTube channel, and there's a video on there called Fun with Data Loggers. And I put temperature data loggers in a bunch of houses, and I show that oversizing equipment is what causes comfort complaints. It causes rooms to drift away. It causes, and in a humid climate, which we're not too susceptible here, but I work with contractors all over the country, Florida and everything else. In a humid climate, if you oversize equipment, it doesn't remove the latent, it doesn't remove the moisture from the air, and you get really bad problems from that. Okay, so oversizing is bad. Undersizing is not as bad. It's not great, but it's not as bad. If we design to really bad conditions, the equipment will be oversized for 99% of the season. Okay. The difference between the indoor and outdoor design temperatures, in California, we design to 68 in the summer, or sorry, in the winter, and 75 in the summer. So we got 68. Think of that as your thermostat set points. Now, people like to set it warmer than 70. I like to heat my house warmer than 68. I mean, but that's what code says. I also have a blog article on my blog, russellking.me, that talks about temperatures and why they're not that big of a deal. If you change the temperature a couple degrees in a load calc, you'll find that it doesn't have a huge impact, but don't mess around with them. You know, Manual J is safe already. It does estimate high on the load calculation, so there's no reason to raise your summer outdoor temperature or raise your winter indoor temperature. But the difference between the indoor temperature, that's your thermostat set point, and that design temperature outside, we call that the delta T. There's a lot of delta T's in HVAC, but this is the design delta T. Okay, and that's what drives a lot of the of the heat transfer in the house, is the delta T. So everything is based on that delta T, and if you change it by just a tiny bit, it doesn't have a huge impact on the overall loads. Other things have a much bigger impact. Window orientation, infiltration, things like that have a much bigger impact. So leave the temperatures alone. Do your load calcs based on what the code requires for the temperatures. All right. Let's see. So load calculations are critical to properly sized heating and cooling equipment. For air conditioners, undersizing will cause the house not to cool well on very hot days. Okay. But there's things you can do to prevent that. Oversizing will cause excess stratification, uneven temperature distribution, plus higher electric bills and shortened equipment life. So oversizing equipment has a lot more potential problems than undersizing equipment. Now, no one wants their house not to work on a really hot day, but why don't we think about the milder days? What about people complaining if your design temperature is 95, what about the days when it's 89 and they're not happy on those days because the equipment's too big, and that's causing stratification, hot upstairs, cold downstairs, uneven temperatures throughout the rooms. If we properly size our equipment, a lot of those things go away. All right. For heat pumps and for furnaces and heat pumps, undersizing will cause the house not to heat well on very cold days, which is not good. Code says you have to have properly sized equipment on your heating. It doesn't necessarily specify that on the cooling side, but it specifies that on the heating side. Undersizing will cause it not to cool well on the really cold days, but oversizing it can cause issues on the mild days. The 99% of the time, when it's less than that, you'll have comfort complaints on those days. So why do we focus on those 1 percentile days and not on the 99 percentile? The importance of good equipment design for equipment sizing. Remember, undersized equipment will work fine on milder days, which is most of the time. Oversized equipment will perform worse on the milder days, which is most of the time. Oversized equipment will cause more comfort complaints than undersized equipment. Okay, it's human nature, and I get caught up in it sometimes too. When you do a load calc and you're picking a piece of equipment and it's right on the borderline, you're like, I'm going to round up a size just to be safe. It's the other way around. You should be looking for reasons to go down a size, okay, not up a size. Oversized equipment will cause more comfort complaints than undersized equipment. The negative impacts of oversized equipment can be reduced by dual speed or variable capacity equipment, that can throttle down on mild days. Okay, that is one way to handle that. But you should still size the equipment as though it was single speed for the design temperatures, and then let the reduced speeds handle the milder days. That's a good way to do it. The negative impacts of both oversized and undersized equipment can be reduced by good duct design and good system airflow. A lot of people don't appreciate that fact that when you start getting comfort complaints in a house, 90% of the times that I've dealt with the problem, it's been caused by oversized equipment that short cycles, and it doesn't let the thermostat sense all the air coming from all the different rooms and things like that. But I've noticed that it's even worse when the ducts are not properly sized. It's equipment size first that's exacerbated by bad duct design. So if you do a good duct design, I like to say good airflow hides a lot of sins. So your balance cannot be perfect, but if you have really good airflow, it'll hide that. You'll never notice that that's a problem. Okay, so good overall airflow is very important. And that's usually the biggest problem I see is undersizing the return ducts, pinches off the entire system. And then you start, oh, that room's starting to get bad, that room's starting to get bad. But then you increase that overall airflow, and it just hides all those other little issues. The negative impacts of undersized equipment can be reduced by improving the house. Okay, so if your equipment's a little too small, think about addressing the demand. Think about making the demand of the house less. Instead of considering putting in bigger air conditioner, bigger furnace, because the equipment's undersized, think about reducing the load of the house first. You should always consider reducing the loads first. Okay, and then increasing capacity of the existing equipment. If you've got existing equipment, check to see if the ducts are properly sized for it. If you improve the airflow of the existing equipment, you'll probably improve its capacity and the comfort of the house as well. So you can do a static pressure test, you can measure the airflow. Obviously, you want to check refrigerant charge and things like that, make sure the fan motor's working well, all that kind of stuff. So you can increase the capacity, but also remember you can decrease the demand of the house. Historically, the most common method of equipment sizing was rule of thumb. How many people have heard the old 500 square feet per ton, or maybe in your area, it's a little more, maybe 600 square feet per ton in the milder climates. But out here in the Valley, 500 square feet per ton has been around forever. Since I've been doing HVAC design, I'm always hearing, well, you're not 500 square feet per ton. You know, and then I have all these examples that just blow that out of the water. When you do rules of thumb like this and trial and error, you know, they'll size the equipment, they'll size the ducts, and they go, oh, the house isn't working well. And the next house, I'm going to go up a size or something like that. And they also don't realize that ducts can be a big cause of the problem too. So when you do use these rules of thumb and trial and error, this almost always leads to oversized equipment that causes a bunch of comfort complaints, and they blame it on undersized equipment. But the problem is really oversized equipment is causing most of these comfort issues. Okay, how do you know? You don't know unless you have something to compare it to. You have to do a load calc to say, oh, I think this equipment's too big, or I think this equipment's too small. Okay, if you don't have a load calc, if you're just going by square footage, you are totally guessing. Okay, having a basis for your design, something to compare to, and what's really important is field testing. Okay, and monitoring is very important too. That feedback, when you do a design, I was really lucky that when I was doing a lot of design work, I had people that worked for the company I worked for out there testing the houses after they were kind of commissioning the houses. So we would design these houses, we'd install them. Then somebody from our team would go out and measure the airflows and send that back to me, and I could compare to our duct sizes and our target airflows and stuff like that. Okay, looks like we got a question. How did we go from BTUs to tons? Good question. So tons, it has nothing to do with weight. It has nothing to do with the weight of the equipment. Tons is a really old term that goes back to when we cool things with blocks of ice. And so a ton of ice had a certain capacity to cool something, to cool vegetables or cool an old train car full of something we needed to keep cool. And so a ton of ice has roughly the capacity of about 12,000 BTUs. So when manufacturers design equipment, they round it to the nearest 6,000 BTUs or half a ton. So they'll say, here's a 1.5 ton, that would be 18,000 BTUs. Here's a 2 ton, that would be about 24,000 BTUs. So that's where it comes from. So a ton is roughly, and I emphasize roughly, 12,000 BTUs, okay? Cooling, 12,000 BTUs of cooling. And again, has nothing to do with the weight of the equipment. All right. Duct design, the importance of good duct design. Since the temperature in the entire house or zone, if it's multiple systems, but you got one system, let's say, serving the entire house, all that house is being sensed by usually one location. You can have remote temperatures, but that's usually a band-aid for not so great a design. But generally speaking, the entire house is being sensed at one location. That system has to run, and all that air goes out to the rooms and makes its way back towards the return, okay? And if you're not properly sizing the ducts, the air is not going to each room proportional to its load, and you're going to get various temperature fluctuations within the house. And the shorter that run cycle is, the worse it's going to be. Shorter run cycles come from oversized equipment. So properly sized equipment is going to run for longer run cycles, which is going to let the house mix better. It's also going to let give the thermostat a better sense of what's going on throughout the entire house. Okay, so how do you do a good duct design? Well, you have to do a room by room load calculation. Instead of just one load for the entire house, which is what we use to size the equipment, we need to know how much air is going to each room. So we got to do a room by room load calculation. That way we know how much air to send to each room. Okay. So target room airflows need to be determined by room airflows. You need to know what the load of the room is relative to the total load, relative to the rest of the house. So if this room is 10% of the total load, guess what? That means it needs 10% of the airflow. Okay. It's all proportional to the room's load. General undersizing of all the ducts in the house, especially the return ducts, like I said, will reduce system airflow, which reduces capacity and efficiency. If you look at the expanded data tables for an air conditioner and you look at the airflows, as the airflow goes down, that's the air blowing across the coil. As the airflow goes down, capacity also goes down. So its ability to cool drops as airflow drops. But if you look right over the next column or two over, you'll also notice that the SEER rating drops as airflow drops. So when you reduce airflow across the coil, not only you're reducing capacity, you're reducing efficiency as well. The amount of electricity it takes to provide that cooling gets worse, okay? And then as I also mentioned, if you, bad airflow will start, when you have bad overall airflow, you start seeing balance problems will start to pop their heads up more and more. But undersizing one or two ducts relative to the rest of the house will result in poor air balance. So balance is the ability to send air to the rooms proportional to each room's load. And if you don't do a good design with that, that's when you start getting hot rooms and cold rooms, hot upstairs, cold downstairs, and stuff like that. Okay. But again, if you have really good airflow and the whole system is moving really well, it hides those things much better. They're much less likely to show their heads. Okay, I always air balancing is kind of like whack-a-mole. You hit one, and another problem pops up over here, and another one pops up over there. But good overall airflow hides these issues. Okay, and but it's still important to know how much air needs to go to different places. You know, you can have a hot room or a cold room that a homeowner is complaining about, and you go out and you measure the airflow and you go, well, I think this flow's too low. How do you know? How do you know what it's supposed to be? You don't unless you have a load calculation. You need to do a load calculation and say, this room needs 10% of the air. It's only getting 5%. Therefore, it's way too low. Okay, so you need those numbers. You need tangible numbers to compare to. And it's not that hard. I'm going to show you, it's not that hard to do. Equipment cannot be properly sized unless you know the load of the house. That's the total demand. Equipment cannot be properly sized unless you know the actual capacity. So when we start talking about capacity, I'll show you that the capacity of a piece of equipment, air conditioner or heat pump, changes when things change. And that's why I said a ton is roughly 12,000 BTUs, because a 2-ton air conditioner in your guys' neck of the woods on the coast puts out a lot more cooling than a 2-ton air conditioner in, say, Death Valley. The same piece of equipment has different cooling in different locations, depending on things like airflow and outdoor temperature and stuff like that. Okay, so you have to know the load and you have to know the actual design capacity of the equipment, not the nominal capacity, not the tons, but the actual design capacity. And then the ability to match those two together is what results in good, comfortable houses. All right, so equipment cannot be properly sized unless you know the load. That's manual J. Equipment cannot be properly sized unless you know the capacity. That's manual S. All right. Then ducts cannot be properly sized unless you know how much air to distribute and where to distribute it. All right. And to do this, you need to know room by room load calcs, and that is manual D. Okay. All right, let's talk about the big picture, the overall design process. What's involved in doing a design on a house? There's 4 basic steps. The first step is to collect information about the house. And that can actually be the most complicated step. That can be the most time-consuming step. It's just gathering the information you need to do a good duct design, okay? Then once you have that information, you do room by room load calcs. Then you select your equipment. Then you tell the software that you're using, and we'll talk about software in a second. You tell the software, I've picked this piece of equipment and I want it to move this much air. All right. You tell that to the software, and the software says, okay, because I did a room by room load calc, I know where that air needs to go. I need to know how much air it needs to move. And that's all done by manual D. So that's the duct design process. So collect information, load calcs, pick your equipment to match those loads, design the duct system to provide adequate air where it needs to go. All right. Sounds complicated, not that complicated. Okay. Software. You're gonna need software. Okay. For the first couple of years, I was doing load this. They didn't have, they had really, really crude spreadsheets. We were doing all this by hand. We would write out the area of the wall. We go to a table, we look up a number, we multiply it out, we get the BTUs for that individual wall. We did that for the entire house. If you're doing that on a room by room basis, it's horrible. It's a terrible process. In the early 90s, software came out, the one on the far left here, RightSoft, that one's been around the longest. Elite came around in the late 90s, maybe early 2000s. Elite came around. They're very similar to RightSoft. And then the newest one is a Quick Model that my company has developed. I'm very familiar with all 3 of these. I have taught on all 3 of these, okay? Whichever one you pick, you're gonna need to take a class or 2 on that software, all right? Software is critical because they're all quite different from each other. You need to take a class on the software. The software have their own, special way of applying manual JS and D. So whichever software you choose, be sure to take a class on it. So when the first step in the process is to collect the information about the house, all right? What you're collecting, what you need are areas of the house, the geometry of the house. You need areas for the ceilings, the walls, the doors, and the floors. Most importantly, the windows. 1 square foot of glass is worth 25 square feet of wall in terms of heat transfer, okay? And that's a safe number. It's maybe even more than that. And not only do you need to know window areas, you need to know the direction they're facing, okay? These surfaces, these areas are what conduct heat into and out of the house. Notice it doesn't say conditioned floor area, like in this image here is a 2-story house. That square footage on the 2nd floor, there's no heat being transferred through that floor to the 1st floor. That's called an adiabatic surface. The temperature at the 2nd floor is assumed to be the same as the temperature of the 1st floor. So there's no heat transfer through that floor on the second floor. So how in the world can that possibly have an impact on the overall load? Well, a bigger house is going to have more wall area. Okay, a bigger house might have more window area. It has nothing to do with the conditioned floor area of the house. Okay, a one-story house with a raised floor, then it does have some impact square footage because there is heat transfer through there. Slab on grade houses, the only heat transfer through a slab on grade house is through the edge of the house, not the middle of the slab, but on the edge. So you could have a giant house with less perimeter and have a lower heat transfer than a tiny house that's really spread out and has lots of perimeter. Okay, so square footage, conditioned square footage has nothing to do. It's very, very low impact on the load of the house. So hopefully I've beat that horse to death. So we want the surfaces that are between conditioned and unconditioned space. So ceilings, walls, doors, floors, and windows. And then of course, we also need orientation of the windows. Okay, got a question here. Does Gypcrete change heat transfer between floors? Not between floors. In order to have heat transfer, you have to have a delta T. So if your top floor is one temperature and we assume the first floor in a good design, they're going to be the same temperature, no delta T, no heat transfer between floors. Just like there's no delta T between two rooms. You can have insulation or no insulation between two rooms and it'll have no impact because it's the same temperature on both sides of the wall. The only time we put insulation between floors, between conditioned space or between walls is for sound, not for heat transfer. Okay. All right. So you'll need to do this. If you're going to do room by room load calcs, you're going to have to keep track of all those areas by room. So you need to know this window goes with this room, this wall goes with this room, this ceiling goes with this room. And you have to do a room calc on individual rooms. And that's a lot of surfaces to keep track of. Okay. That's where software is absolutely critical to do that. All right. So the goal is to accurately estimate conduction, convection, and radiation between the inside of the house and the outside of the house. Okay. So conduction is heat conducting through a solid surface. Convection is heat passing by moving air, and radiation is heat coming in through light. Okay. So that's where solar gains becomes very important. You have to do this for the winter and you have to do this for the summer. Now, radiation is ignored in the winter. Solar gains are not counted in the winter. Think of when you're doing your winter load calc. When is it the coldest? It's the coldest at night. So no solar gains. Okay. Summer, absolutely. Some solar gains can be one of the largest loads on a house is solar gains. Sun shining through windows. All right. But the point is, you need all those areas, and then you have to calculate convection, conduction, radiation, both for winter and for summer, but radiation is ignored for winter. Okay. If you're designing a system for a new house, you will probably have a set of plans. More than that, you'll probably have a set of energy compliance documents. If you're doing it in California, all new construction will get a Title 24, and that's a nice, concise summary of all the energy features on that house. If you have a set of plans and you have your Title 24 calcs, you pretty much have the information you need to do a load calc right then and there. Okay. If you're designing for an existing system, it's a lot more work to get all that information. You may need to go out and actually sketch a floor plan of the house. Okay. Just in the last couple of years, some really, really cool apps have come out. And the one that I really like is called QBCasa. And there you see it on the screen. QB.casa. That's their actual website. It's not .com, it's .casa. And the app is called QBCasa. And it's free. It's incredible. It's free. It's a phone app, and you put it on your phone, and you basically start in one corner inside your house, and you videotape your baseboards throughout your entire house. You send that off, and they guarantee a 24-hour turnaround. It usually comes back faster than that. And you get a floor plan, not like the one you see on the screen. That's a hand-drawn one. You get a floor plan that looks more like this from videotaping your baseboards. It doesn't have the cabinets and stuff like that in it, but it looks like an architect drew it. It's phenomenal. I've trained hundreds of people how to go out to a house with a tape measure and create a floor plan of the house. I wish I would have had QBCasa back then. And there's several other ones too, but I'm a big fan of QBCasa, mainly because it's free. to get a basic floor plan back. Okay, so definitely check that out. If you're not familiar with QB Casa, you can buy me a beer later. You'll really appreciate it. All right. So then you're gonna have to figure out. We're talking existing houses, so you got your floor plan now, and that floor plan can be used to get your areas. Now you need to know what kind of surfaces. So you have to do a little research. You can look at the age of the house. You can go out. You can probe in the wall with a. We always trained to use a bamboo teriyaki stick. A barbecue skewer, a bamboo. You take a knife and you put a little fork in the end of it. You poke that in through an outlet plate cover. You pull the outlet plate cover off and you poke it in there and you twist it and pull it out, and you can see what kind of insulation's inside there, whether it's bad or blown in or whatever. And then based on the age of the house, you can kind of get an idea. You can stand in an open doorway, put one hand on the inside, put one hand on the outside, and tell whether it's a 2x6 or a 2x4 wall. There's a lot of things you can do. And you don't have to be perfect, okay? Keep that in mind. There's a lot of stuff. Load calc is a very crude calculation, so don't stress out over precision. If you do a rough load calc, you're so much farther ahead than someone who uses square footage to size equipment. Okay, you don't have to be perfect. Keep that in mind, and don't stress out over some of the precision. When I teach the more involved HVAC design classes, I have a saying I use a lot, and that is, don't waste time splitting hairs, because your job is to shave heads. You need to get this done. You need to do it quickly. So don't get caught up in these little minutia details. Just make your best guess and move on. And then if you're not sure, guess one way, do the load calc, guess another way, do the load calc again. Like if you're not sure what's in the wall, if you're not sure if it's R13 or R15, run the loads with R13, write it down, run the loads with R15, write it down. And what you'll find is the difference in loads probably isn't enough to change the equipment size. Okay. So always do those little things. Get to know the software, get to know what's important and what's not important. Okay. Windows are important. Window area, and then the type of windows. If it's dual pane versus single pane, that's easy to tell. Metal frame versus vinyl frame, that's easy to tell. There's some ways to check to see if it's low E or not. That can have a big impact. There's little things. It looks like a little. It looks like a stud finder. You put it on a window and you press a button. It'll tell you if it has a low E coating on it or not. Okay, but you don't need to know, is it a U of 0.35 or a U of 0.37? That's not going to make a big difference. It might make a big difference in the energy compliance, but it's not going to make a big difference on the load calc. You just need to know the basic kind of window. And then again, run one way, run it again, see if it makes a big difference in the load calcs. All right, for existing homes, you'll have to visit the house to determine these features. For new homes, this will be in the energy compliance documentation. Okay. Now, do keep in mind that a lot of times the Title 24 calcs is the minimum to what's required, and sometimes they'll get it to where the house just barely complies to the energy code to give them flexibility, but then they install something that's a lot better. If that's true, you need to ask them and say, hey, is this house gonna be a lot tighter than the minimum, or is this house gonna have much better windows than what it says on your Title 24 calculations? It's always worth finding out that kind of stuff too. Okay. All right. And then there's a few things you're just gonna have to make some judgment calls on. And for existing homes, the two big ones is duct leakage and infiltration. Now, duct leakage is not so difficult, but infiltration, well, both of these, whatever you assume for duct leakage and infiltration, you're gonna wanna test that. For infiltration, you're gonna wanna test it before, and for duct leakage, you're gonna wanna test it after you install the equipment, okay? So in California, duct leakage is required to be improved as part of a major work being done on an HVAC system, okay? For substantially new systems in California, a new house is obviously a new system. For an existing house, if you replace all the ducts and all the equipment, that's considered a new system. And so you have to meet the new system duct sealing requirements. But they say if it's more than 75% new ducts. So if you leave a few ducts, change everything else, that is considered a new system. And the allowed leakage for a new system is 5%. For altered systems, you have to get it down to 10%, but there are exceptions. If the ducts have asbestos in them and things like that, or if the ducts are not accessible, it may not be 10%. So if it's possible that you won't be able to get it down to 10%, you may want to pre-test the ducts to see how leaky they are. So that's a judgment call, okay? But the more field testing you can do to verify these numbers, the better off you are. I actually recommend doing a blower door test just to change out the furnace and air conditioner. Now, even if you're not touching the ducts, I highly recommend that you do a blower door test. And I know a lot of contractors that do that. Like I said, I work with contractors. I sell software all over the country, and I work with a lot of contractors. I'm on a lot of Facebook groups. I'm on a lot of blogs. I talk to a lot of organizations. I go to a lot of conferences. And I'm learning now that in California is actually kind of behind the curve, and it's a little surprising actually. Florida, Louisiana, Mississippi, North Carolina, a lot of the humid climates, we are really lucky in California that it's a dry climate. When you throw humidity into the equation, it gets much more complicated. And humidity comes from leakage when a house leaks. So I know a lot of contractors in other states who do a blower door test on a house because they've learned that infiltration, you can't look at a house and tell how leaky it is. It's impossible. So you've got to test it. A blower door test only takes a few minutes to do a blower door test, and it impresses the heck out of the homeowners. They go, "Wow, I'm having these things bid, and you're the only contractor who even mentioned the blower door, and it can be impressive." Okay, let's see. Here's a comment in here, or you may want to consider changing the duct system if the leak is more than 5% maximum. Yes, you're doing a load calculation to do a system design. Sometimes that means recommending changing the duct system as part of your design. Absolutely. I agree with that 100%. I will tell you from my experience and from some studies that were done funded by the California Energy Commission, the average house in California, the equipment is oversized and the ducts are undersized. Now, if you can go out to a house and you can do a load calculation and show them that they don't need a 4-ton air conditioner, a 3-ton will work just fine, then that 3-ton air conditioner might work better with the ducts. The ducts might be properly sized for the 3-ton when they were undersized for the existing 4-ton. It's that sort of a thing that you really need to do, and you can do. It just takes time to do it, okay? But if you get good at it, and I know contractors who will charge a homeowner as part of the bidding process and say, "Hey, you want me to do a good design, you'll pay me to do a good design." And so there's ways to get things paid for like that too. So when you change out the duct system, the new code says seal and insulate the attic. Yes, that's in the brand new. Thanks, Mike. That's in the brand new code. In certain climate zones, that it does require, if you're getting up in the attic and the ducts are in the attic, that you have to seal and insulate the ceiling too, as part of Title 24. And that's new. I don't think that's in the 3C REN climate zones, so I think that's more Central Valley, hotter climate zones. All right, infiltration can have a dramatic impact on load counts. Yes, 100%. It is very bad if it is very bad. So if you go out and you do a pre-test, you do a blower door test on a house, and the house is super, super leaky, really bad. And one common rule of thumb is if you do a blower door test, the number you get from the blower door is called a CFM 50 number. That's the number that it gives you. If the CFM 50 is higher than the square footage of the house, that's considered to be a very leaky house. Okay. So if you do a blower door test and the house is really, really leaky, all right, should you use that really, really leaky number in your load calculations? I say no. I say you're not doing the homeowner any service by assuming a really, really leaky infiltration in your load counts. What should you do instead? You should recommend to the homeowner that they seal that house, reduce that leakage. It's like I've tested a house one time that was really leaky, and we went around, we found out it had a broken window. It was an empty house, and someone had broken out one of the windows. And if I did a blower door test and it's really leaky, should I assume that number in my load counts? No, you replace that window. All right. I've tested houses that were leakier than the house that had the broken window, but they had no broken windows. The house was broken. There was something wrong with the house. Don't use really leaky infiltration in your load calculations. Seal the house first. Okay. That's just my opinion. But if you don't, you're not doing the homeowner any service. You're making them put in a much bigger piece of equipment than they need when you could have them put in smaller equipment and use less energy. All right. Okay. So step one was collecting information. That's what we talked about. Step two is to do load calculations. That's what we're going to talk about next. And then step three will be selecting the equipment. That's what we'll talk about after that. And then next class on Thursday, we'll talk about manual D. So again, the 4 basic steps of design process is collect information, do your load calcs, select your equipment, design the duct system. All right, let's talk about manual J load calcs. There are 2 basic kinds of load calcs. All right, let's see, you got some comments here. Air seal and recheck, especially if going to gas, from gas to a heat pump. Yes, remember that's the supply versus demand. I'm glad you guys are getting that, supply versus demand. Your typical HVAC contractor will go out to a house, and you know the old expression, if you're a hammer, everything looks like a nail. All right, and they'll say, oh, you're having issues on your house, I think you need a bigger piece of equipment. A building performance contractor understands that there's 2 sides to the equation. And instead of just raising the capacity, how about lower the load? Okay, bring the load down to what it should be. All right, so very, very important. Okay, so there are 2 basic kinds of load calculations. One is a whole house load calculation, also called a block load, and the other is room by room. So a whole house load calculation is all the rooms lumped into one number, and that's what you use to size equipment. Now, if it's a 2-zone house, you take all the rooms for one zone, you size that piece of equipment, all the rooms for the other zone, you size that piece of equipment. But we're just going to assume that for now, it's one system per house, okay? And that works fine for sizing equipment. But if you're going to design the ducts or evaluate the existing duct system, you really need to do it room by room. There's a lot of software out there that'll only do block loads. CoolCalc is one. There's a few others that'll do block load, which is fine. That's like the bare minimum to get your permit if you have to do a load calc. But if you're going to evaluate those ducts, if you design ducts especially, you've got to do room by room loads. And it's almost as easy in the 3 software programs I showed you. It's pretty much, if you're going to do it, you might as well do a load calc. It's not that much more work to do room by room load calc compared to doing a block load. Okay. All right. So this is just an example of a printout that you'll see for Sacramento. It's got your latitude, altitude, temperature range, relative humidity, indoor stuff. Here's your sign temperatures. 26 outside, 98 in the summer, 26 in the winter. Your winter set point is 68, summer set point 75. That's required by code in California. These numbers come out of it's reference appendix JA2. Reference appendix JA2 is where we get these numbers from. Okay. And that's good enough. But room by room load calcs break the loads up by individual rooms. So this is a printout from Quick Model Software. Here's a list of all the rooms, what block or zone that it's attached to, the floor area, the volume, what kind of room it is, how many people are in those rooms. And then here's your heating load by room. Okay. Here's your cooling load by room. Now you take this number 6047 and you divide it by your total, and you get a fraction 0.217. So what this is saying is this room, the master bedroom, has a room load of 6,047, which just happens to be 21.7% of the total. The fraction is 0.217. In other words, 21.7%. So it needs 21.7% of the air. So we take this fraction and to multiply it times the target airflow, which we are going to tell it in the manual S stuff, 1200 CFM, and we get 261 CFM. And that's how we size the ducts, because we know this room is 21.7% of the load. It needs 21.7% of the air, which is 261. And we want to make sure it gets that air. So we're going to size the duct to deliver that 261 CFM. But we have heating mode and cooling mode are different. Occasionally, the heating load target airflow is higher than the cooling load target airflow. Okay. So we need to design the higher of the two. So this last column here, and the software does this all automatically for you. But this last column here looks at the cooling CFM and the heating CFM, and it picks the higher of the two. And if you go down and you look at the total, 1232 is higher than 1200. So we know that there was a couple rooms that had higher heating CFM. And I can see one right here. The cooling CFM was 48, but we used 65 because the heating CFM was 65. So this little room here, the utility room, it's usually smaller rooms where this happens. The utility room wants 65 in the heating mode and only 48 in the in the summer mode. So we want to design to the higher of the two. So that's what we do. We'll put in a duct that will deliver the 65. And then people say, well, then it doesn't balance out in the wintertime and the summertime. Trust me, those sorts of things, if you do a good airflow, you won't notice that kind of stuff. All that stuff will be hidden. You could be plus or minus 20% on your airflows, and chances are no one's even going to notice. Okay, if you have good airflow, good overall airflow. Okay, all right. There are load calculations for both heating, which is in the winter, and cooling, which is in the summer. Again, winter is the heat leaving the house, summer is the heat coming into the house. Let's look at heating load first, because those are more simple. And this is an example printout here. You can see that the heating load was this number here. And then cooling gets even more complicated because we're talking about sensible and latent. All right, but the total cooling load is down here, 26,131. And then you'll see that it's broken out by windows, walls, ceiling. That's always useful because you can come in here and you look at this and go, wow, why is the floor such a big number? And that's because it's a slab on grade house with uninsulated slab edge. A lot of people don't realize that. Slab houses are great for cooling. It's this nice thermal mass for cooling. But in the winter, slab on grade houses, if you don't insulate that slab edge, it loses a lot of heat out that slab edge. Okay. And you know that by looking at these things. There's also some pretty cool pie charts you can print out and look at and stuff like that. And then over here, look at the floor load is 0. There's no floor load because slab on grade, the ground is actually cooler than the house. And so the slab actually helps cool the house, but we don't give it credit. We just kind of call it a wash. All right. Infiltration loads, all this other stuff. Some people go in there and stuff like that. That's just kind of a sample printout. Okay. Heating load calculation is the sum of all the B2 losses, convection, conduction, radiation, that occur when it's a certain delta T. And that delta T just happens to be 42 for this example. So it's 68 minus 68 degrees inside minus whatever the outdoor temperature was. 46, 26, 29, I forget. Sorry, let me go back here. Here we go. 26, 68. Is that the same one? 26, no, yeah, that is. That gives us our 42. There we go. Okay, simple math, Russ. Come on, you can do it. All right, so that's what drives this number here. And like I said, we can go back and we can fiddle with some of the stuff. And I highly, highly recommend you do that. You do your load calc, you get a number and you say, what if the wall insulations actually are 15 instead of our 13? Go back and change it, run your load calc, see if it made a difference. And what you'll find is, look at the wall load is a fairly small number, 5,399. So if that number only changes a little bit, this number is only going to change a little bit. Okay, so do those kinds of things. Very, very important, and it'll have an impact on the summer side too. Okay, so delta T is what drives the heating load. It's determined by the two temperatures, indoor and outdoor. For heating, assume that this occurs at night, so there's no solar gains. Okay, so you don't have to worry about window direction when you're doing your winter load calculation. It's nighttime. There's no sun shining through. But that is absolutely not true for summer. Cooling loads are similar, except they are more complicated because solar gains are not ignored. All right, we have to look at the direction that the windows face. Let's see, can you go into sizing, taking latent and sensible into account? Equipment uses numbers that don't really match up with the arid climates, and so I end up having a hard time getting that to line up. When we talk about manual S, we'll get to that. That's equipment selection. But for the load side of it, the load will tell you over here. So of this 26,131, that's our total load. Of that load, 24,449 is sensible. Sensible is the load that changes temperature. And that's what we care about in a dry climate, the load that changes the temperature. And a lot of people says, well, what else is there? Well, in a humid climate, part of your capacity of your air conditioner is used up drying the air, not changing the temperature, but drying the air. In California, we're lucky, we're a dry climate, and that's called the drying the air is called the latent load. So you'll see here that the sensible load is 2449, the latent load is only 1683. That's a really small percent. In fact, if you take that percent, let's do that really quick. I'll take this total latent load, 1683, and I'll divide it by the total cooling load, 26131, and I get 0.064. Subtract 1 from that. That's a 93%, what we call a sensible heat ratio, 93%. Anything above 90 is a really dry climate, okay? So we don't have a huge latent load. Now, when we go pick a piece of equipment, that equipment is going to have sensible capacity and latent capacity. Sensible capacity and latent. So we got sensible load, latent load, really tiny, sensible capacity, latent capacity. In a dry climate, we want the sensible to match. We can pretty much ignore the latent. In a humid climate, we want the sensible to match, but then we got to go look at the latent and make sure it has enough latent capacity too, which we don't have to do in most of California, 99% of California. Okay, we'll talk a little bit more about that in the manual S part. Okay, so what makes them so complicated is you got to worry about window orientations is another big deal. Cooling loads and the subsequent sizing of equipment is more precise than heating loads typically. So there's a lot more stuff to think about. And then depending on the software, you must input all the surface geometry either by typing it in, which some software still do. So you'll have to manually measure. You'll look at the floor plans. You'll say, okay, this wall is this many square feet, and you'll type that number in. Some of the software, RightSoft and Elite, you draw the footprint of the rooms, and then you tell it the height, and it will it'll do the wall area calculations for you. In Quick Model, you build the house out of 3D boxes. You don't have to know CAD. You just build the house out of boxes, and they're stretchable boxes, and they bump into each other, and you build the house in 3D, and it does all the calculations. So you're getting all that area geometry information from the software one way or the other, okay? And that it just needs to be reasonably accurate. And then the software will use that information and it'll say, okay, I've got this much wall, it's this kind of wall. It actually goes to the Manual J book that's built into the software, and it pulls a number out of the tables and it multiplies it together to give you a BTU. So that's all done individually. So you can see how many walls are in a pretty simple house. I think this is cut off at the bottom. I think there's like 36 walls in this house. So that's a lot of stuff to keep track of. Okay, so we got our load counts. The total load we're gonna use the size of our equipment. The individual room loads we're gonna use the size of the ducts. We'll do that on Thursday when we do Manual D. But let's pick a piece of equipment. So Manual S, equipment selection. Once the room by room loads are done, you add those up to get your block load, and that's what we use to size the equipment. Okay. Then we select the equipment. So the example we're gonna use is going to be a pretty standard, we'll call it a horizontal unit up in the attic. We'll talk a little bit more about, ducted and ductless mini splits and stuff like that, but let's focus on your more traditional condenser coil. This could be a furnace, or it could be a more traditional style heat pump, the older style heat pumps with a big fan coil unit. Okay, let's kind of focus on that first. If it turns out that the load is too big for a single piece of equipment, then you break it into zones. Okay, I mentioned that earlier. You can have multiple zones. You might want to split upstairs, downstairs. Obviously that's more expensive to do it that way, to have multiple pieces of equipment, but it works quite well if you've got the room to do it. So those are the sorts of things that come into play. But let's just say we've got a load calc and there's a piece of equipment that will match that load. It's not bigger than a 5-ton. Okay. Heat pumps. So there are many good reasons for converting from gas to heat pumps, not the least of which is all the money they're throwing at it, rebates and incentives and things like that. But there's a lot of myths about heat pumps. A lot of people say, oh, they blow cold air, all this other stuff. Those are design problems. Those are not equipment problems. Those are design problems. So you've got to do a good design if you want a heat pump to work correctly. So it's that much more important that you do an accurate load calc. It's that much more important that you do room by room load calcs. It's that much more important that you do good duct design and have good airflow. Okay. A well-designed heat pump works wonderfully. It works great. Okay. The first house that my wife and I bought right after we got married had a heat pump in it. And it was supposed to be an all-electric subdivision back in the day. This is back in the 80s. But they ended up putting a gas water heater in it, but they left the heat pump in the house anyways. But it's a brand new house, poorly designed. Ducts were undersized. Heat pump was probably bigger than it was bigger than it needed to be. The ducts were poorly designed. I got up there and fixed a bunch of stuff. I put better registers on. I improved the airflow. I put a bigger return in it and all this other stuff. I didn't want to downsize the equipment. It wasn't super oversized, but it was a little oversized. And then once I got it all dialed in, it worked great. My neighbors were miserable. They had the exact same floor plan as us. They hated the heat pump. We loved it. We never noticed it came on. The house was just always comfortable. It was quiet. We didn't even set it back. We didn't use setback. We just set it at a certain temperature and left it. It was great. This was in the Sacramento area. So the point, and I know people, I have a friend who lives in Minnesota and has a heat pump in his house and it's working great. Okay. So it's not a heat pump problem. It's a design problem when you hear about all these problems. The vast majority of these problems were due to bad duct design, okay, not properly sizing the ducts. Heat pumps have improved dramatically over the last few years. So your dad's heat pump, your grandpa's heat pump is very different. The heat pump that I had in my house in the 80s is very different than the heat pumps that are available today. Most of them are inverter driven, variable speed, multi-speed. They've improved the controls a lot. They've improved the compressors a lot. So they're much better than they used to be. So heat pumps can work great. California is the perfect climate, especially on the coast. Coastal California is like the perfect climate for heat pumps. It really is. And they're super efficient. And one of the reasons they're so efficient is because they don't create heat. Heat pumps don't create heat. They move heat. They move heat that already exists and they just condense it and they move it somewhere else. And because it takes less electricity to move heat than it does to create heat, they're super efficient. Okay. They work at a much lower outdoor temperature than people realize. And chances are you don't even need electric backup strips. I know a lot of contractors who the homeowners insist that they put electric backup strips in the house. The homeowners put them in, or sorry, the contractors put them in, but they don't hook them up. They leave them unhooked. Okay, not even turned on. They're in there. They just don't have them plugged in. And the homeowners go, "Oh, it's working great. It's working great." And they never come back. They say, "Okay, if they start complaining, I'll come back and I'll turn the heat strips on." And they never do. They never come back. If you properly size a heat pump to meet the heating load, okay, without it being too big for the cooling load, they'll work great. The heat strips should never come on. Okay, except maybe in the defrost cycle, and if you use backup strips and something like that. You recommend using a surge protector with heat pumps? I would defer to the manufacturer's specs on that. I typically don't specify that unless the manufacturer suggests it. And if you're not putting in heat strips, it's typically, I believe, less critical for that. But it's to protect the equipment. Some of the new heat pumps have very, very sensitive electronic controls in them, so it's almost like a computer, hooked up to it. So probably so. But again, I defer to the manufacturer specs on it. There's no code, and it's not mentioned in manual JS or D about it. So I defer to manufacturer specs on that. All right. Sizing heat pumps is certainly more complex than sizing furnaces. I like to call furnaces dumb beasts. You turn them in, hook up the gas, turn them on, they give heat. And the only thing that's going to affect how much heat's coming out could be altitude. The higher you go, the less heat it puts out, but it's not a huge impact until you get up to like 6,000-7,000 feet. But heat pumps are more sensitive, so you do have to be more careful. Manual S covers heat pump sizing very well. By the way, there's a new Manual S coming out. All right, it's supposed to be out by the end of this year, and it focuses a lot more on heat pumps. But there's also a manual H. ACCA has a manual called Manual H that goes into heat pumps in a lot more detail. All right. Let's see here. I'm just checking my slides. I'm doing okay on time. I got about 18 minutes left. We're doing good. Manual S covers heat pump sizing very well. Manual H goes into even more detail. So because the air conditioner and heat pump are the same condenser, you should size for air conditioning first and then check to confirm that it is not undersized for heating. If it is, you can go to a larger condenser. So that's where backup strips start coming into play. But I'm 90% sure that in most of coastal California, if you size your condenser for your heating load, all you have to do is just make sure that it's not oversized for cooling. Okay. And that's the recommendation that's coming out. That's going to be by the way, that's going to be the recommendation in the 2025 Energy Code, is that you size your heat pump to match the heating load. And then you look at the cooling load and make sure that it's not way oversized. If it is way oversized, there's some things you can do. You can put in a variable speed, all right, and then size it for cooling load and things like that. Okay. That's one of the downsides to heat pumps, and why it's more complicated is that you only got one condenser and it gives you a certain amount of cooling and a certain amount of heating, and that's your choice. That's it. Okay. In the old days, we would size to cooling and make up the difference with electric strips. They're definitely getting away from that. And like I said, in most of California, you don't need to do that. You don't need electric strips. Okay. But that's an entire class all to itself to get into how heat pumps are sized. But just suffice it to say, heat pumps are a bit more complicated. You got to spend a little bit more time. And so if you're an installer and you're dealing with, one or two different brands that you use all the time, get to know those brands, get to understand how to read the manufacturer's specs, understand how to read what impacts the heating output and the cooling output. And it's going to be a few things that I'm about to show you. Okay. Undersizing heat pumps may cause them to run excessively and potentially on backup electric strips. You don't want to do that. Oversizing issues on the cooling side can be mitigated by good duct design and good airflow. All right. So even if your air conditioner is a bit oversized, if you have good airflow, good duct design, you won't notice it. Okay. And then again, variable speed equipment. Selecting a gas furnace is easy. All right. You got your heating load. You pick a heating capacity that's a little bit bigger than your heating load, and that's what you need. But don't forget that your furnace may also provide your cooling airflow as well. Let's see. Question here. Oh, Mike, do you have to buy all the ACCA manuals? No, but I recommend that you buy Manual J, Manual S, and Manual D. Okay, and they're not cheap. They are not cheap, but you can find them. You can find them online, sometimes used. Here's mine right here. Let me grab them real quick. I would wait on Manual S, because Manual S is being rewritten. Here's my 3 manuals, so I can get it to where you can focus and get close to my face. Manual J, S, and D. Okay, they're pretty beefy books, right? The most important one is Manual J, because when you do a load calculation using the software, I always recommend that you print out the reports from your Manual J and you look at the Manual J book and make sure that it's doing what you think it's doing, that it's pulling the right value from the right table and things like that. So the Manual J is an important quality assurance tool. Manual D, there's some appendices in there that's useful for equivalent lengths of fittings and stuff like that. Manual S, I would wait until the new Manual S comes out, honestly, to buy that. Okay. All right, whatever the load is, pick the furnace at the high. I got that. Don't forget the furnace is also the air handler. So sometimes you have to go to a bigger furnace in order to get the right size fan to handle the airflow. You guys don't have to worry as much about that in the coastal climates that you guys are in. But when you get back inland, you guys get into some pretty hot climate zones, so you will have to take that into consideration. All right. Here's where you really need to take an entire class on Manual S, because remember I said whatever brand equipment get to learn to use to read the manuals, read the tables. There's something all heat pump and air conditioning manufacturers put out. It's called the OEM, original equipment manufacturers, the OEM expanded data tables. There, or it goes by a variety of names: expanded capacity tables, expanded data, expanded. It's going to say expanded something, and it's just showing you that that X ton piece of equipment isn't really giving you 12,000 BTUs per ton, or 12,000 BTUs per ton. It's giving you something else because there's things that affect that. So what affects it? Well, look at the tables. If you look at the tables, you got outdoor ambient temperature, 65, 75, 85, 95, it goes up. So outdoor temperature affects it. Airflow, 525, 610, 675. Indoor dry bulb, 70, 75. Indoor wet bulb affects it. So outdoor temperature, indoor temperature, airflow, indoor wet bulb, indoor dry bulb, indoor wet bulb. So there's 4 things that affect an air conditioner's capacity. Some of those things you just assume, okay. Indoor dry bulb, we typically assume 63. Indoor wet bulb, we usually assume 63. Indoor dry bulb, 75. That's our thermostat setting. That's what we did our load calcs to, was 75 degrees indoor. The outdoor, you do your outdoor design temperature. Unfortunately, it's in increments of 5s and 10s. You have to interpolate. So this has 95. I think the next table over is 110, okay, or 105 and 115. So if your design temperature, outdoor design temperature is 98, you're gonna have to interpolate between the 95 and the 105. It's not that hard to do. A little spreadsheet, you can do it on your calculator, okay. But anyways, and by the way, this highlighted number here, these are the numbers that the equipment is tested at. These are called the AHRI conditions, okay. And that's it. That's what it's tested at, and that's how they get their. Is it a 3 ton? Is it 3.5 ton? Is it 2 ton? Is it 2.5 ton? Is based on these capacities down here, okay. And then as the design condition, the actual conditions that we install it at change, the capacity changes, okay. Not only does your sensible capacity change, but your latent capacity changes too. So that's all manual S. That's, like I said, that's an entire class unto itself. But it's something you need to get good at. And a lot of manufacturers will help you. A lot of supply houses will help you do this, but you got to learn to do it yourself. Okay, it's very important, because if you just say, oh, it's a 2-ton piece of equipment, and I'm going to put this 2 ton in because it's a load calc, and the ton is 24,000, ton is 12,000 BTUs, you're going to be way off. You're going to be way off on your sizing. All right. So again, the things that affect the air conditioner's capacity, its ability to cool, is affected by the outdoor temperature. Where's the condenser located? The amount of air blowing across the coil. In a dry climate, we usually shoot for 400 CFM per ton or better. Higher is actually better. The more airflow you have, the more capacity you have, the more efficient it is. In a humid climate, too much air has less latent removal. So in a humid climate, they want to shoot for around 350 CFM per ton. Guess what? In California, 350 is the absolute minimum. You have to test a new system and have at least 350. I would design to 450 or 500 CFM per ton if I could, okay, if there was equipment to do that. So higher is better on the airflow, but let's just say, and it's a general rule of thumb, but let's just say around 400 CFM per ton, okay? More is better in a dry climate. The indoor temperature, the air that's being pulled up through the return, that has an impact on it. And then the indoor humidity, that has an impact on it as well. Okay. Again, we're a dry climate. We don't usually have those issues, but this is the indoor humidity. So one of the very few times I've ever had issues in a system that I designed that had humidity issues was occupant behavior. It was a house in Las Vegas of all places, and they constantly cooked noodles and they constantly had boiling water on the stove. They had like 30 houseplants in the house. They had 2 giant fish tanks in their house, and they took showers all the time, and they never used their bathroom exhaust fans. So this humidity built up inside this house, and it was making them uncomfortable. that was an occupant behavior issue. I told them they absolutely had to run their exhaust fans. They had to run their kitchen exhaust fan and get that humidity out of the house. Okay. But never ever have I had humidity issues caused by the outdoor humidity leaking into the house. Okay. Las Vegas actually has negative humidity. The outdoor humidity is actually less than the indoor design humidity or wet bulb. Okay. Okay. Airflow. So one of the ones I mentioned here, airflow across the coil. I mentioned that 400 CFM per ton is a ballpark. More is better in a dry climate. Okay. The airflow is affected by what? It's affected by the ducts. You've got a fan that's going to give you a certain amount of airflow, but if you start restricting the ducts, that airflow is going to go down. Okay. And you can look in a fan, the air handler data tables and show how much air it's going to give you at certain static pressures. So you see how much air it wants to give, you want to have at 400 CFM per ton, and you see what static pressure it takes to give you that much airflow. Then you want to design your ducts to ensure that static pressure is maintained when you turn the system on in that duct system. Okay. So that's going to be the next segue into manual D. So this means that duct sizing can have a big impact on cooling capacity. If you undersize your ducts, your air conditioner doesn't work as well. All right. Oversizing air conditioners and undersizing ducts is a very, very common problem. And I do a lot of what I call comfort diagnostics. That's going out to a house, trying to figure out why the homeowner's not comfortable. When the installer says it's working fine, the equipment's working fine, I don't know why they're not comfortable. Can you come help me figure out why they're not comfortable? The vast majority of times, it's two things: oversized equipment, undersized ducts. Okay. We got a question here. Wouldn't the airflow be a more common reason for mechanically zoning as opposed to a high load? Good question. Zoning a house, having multiple systems serving a single house, to me is more about thermostats. Can you put a single thermostat in that house that's going to do a good job sensing that house? And a lot of times upstairs, downstairs is a big problem. So you may want to zone upstairs, downstairs. It's not so much how much air I can send, it's how well a thermostat is going to handle. I did a lot of designs on some very big homes in Las Vegas, big one-story houses, these big, U-shaped houses, giant U-shaped houses where a 5-ton system would handle this big house. Okay. But I wasn't comfortable putting a thermostat way over here and hoping that that thermostat would serve the opposite side of that giant horseshoe shaped house. And so even though a single system would serve that house, the load, it was a control issue. And so we split it into 2 zones. Okay. So those sorts of things come into play. Getting over 2000 CFM is hard to do. It can be, but I don't look at the CFM. I look at the load. I say, what is the load of this house? What piece of equipment can handle that load? And if one piece of equipment can't handle it, or if it's a zoning issue, like I said, then I split it into two zones. I don't look so much as this at the CFM. The CFM is going to be what it is in order to get a certain capacity out of the system. Okay. So thanks, Greg. That's more what I look at. I look at the load, I look at the capacity of the system at around 400 CFM per ton, and I say, will it handle that load? If not, then I think about splitting it into 2. But I'll tell you this, houses are so efficient these days that I don't think I would ever design a 5-ton system ever again on a new house. New houses are so efficient that a 5-ton system will handle like a 4,500 square foot house these days. And that's just too big for one piece of equipment. So anyways, that's kind of another topic. All right. So oversizing air conditioner and undersized ducts, very common problem. Don't do it. I can walk into a house, I can interview the homeowners, and I can almost right away say, I bet I know what the problem is. Your equipment's too big, your ducts are too small. 90% of the time, that's the case. Okay. So a good design will prevent that. A good design will cause you to put in a smaller piece of equipment and say, ooh, I need bigger ducts. Okay. And then you won't have those issues. All right. So summary. So we talked about the ACCA manuals. Manual JS and D are the main ones. There's a bunch of other ones to help you Don't forget those QI/QM standards. It's a little packet, it's a little PDF file. Very, very useful tools, great resources. We talk about capacity versus load. Capacity is what the equipment gives you. The load is what the house needs. You can play with both of those numbers. A good home performance contractor will look at the load first and say, how can we reduce that load? And then they'll look at the equipment and say, what size equipment do we need to meet that smaller load? All right. We talk about oversizing versus undersizing. Then we did an overview of the HVAC design process. It's got 4 basic steps. Collect the information that, like I said, can be the most complicated one on an existing home at least. Perform the loads, select the equipment to meet the loads, zone it if you need to, design the duct system, which we will go into in great detail on Thursday. We hope you'll stick around, come back on Thursday, and we go into manual D. How do we get the air to where it needs to go? We'll talk about, we'll talk about how to use a ductulator, which is actually built into the software. Here's my ductulator collection. Okay, I've got a bunch of them. This is my favorite one. This is the ACCA wheel. It does different kinds of ducts. We'll talk about friction rate. We'll talk about airflow. We'll talk about flex duct versus sheet metal ducts, all that good stuff, and the importance of getting all that to work. So that'll be on Thursday. And then today we talked about load calculation. We talked about equipment selection. I hope that's good. Here is my email. Yes, Mike, I know you have questions, and Mike, you of all people have my email. You have my personal email, Mike. Mike's actually one of our software users. Feel free, if you have any questions between now and Thursday, don't hesitate. russ@coda-energy.com. I'm sure Gray's got an email you can send questions to, and they can get it forwarded out to me. So there you go.
Awesome. Thank you so much, Russ. And thank you all for attending. I am just going to launch a quick poll. It's optional. Just helps give us some reviews on how useful this meeting was for you. But again, we hope to see you on Thursday at the same time. And then I will be sure to send a recording and the slides from today as well as Thursday. Also, feel free to check out our other upcoming courses. We have an Introduction to Passive House course coming up on the 1st, a course all about mechanical ventilation. We'll be diving into the Cal Green codes. And then we have our High Performance Building Fundamentals series going on right now, which includes that Crafting High Performance Enclosures course. And then we're finishing out our energy code series for this part of the year with non-residential on the 17th of next month. So if you have any questions, please feel free to email me. My email is listed there, and I will put it in the chat. Yes, Nancy, I will be sending a copy of the presentation. You should see a follow-up email tomorrow in your inbox. All right. Thank you so much, everyone. I hope you have a great rest of your day and hope to see you on Thursday. And thanks again, Russ. All right. Bye all.
Thank you.